In this quick video, I'm just going to go through what Year 9 should have learned from Easter to May half term in chemistry. The first task that I set was to revisit the electron structures, which you should have done just after Christmas, and it's where the electrons fit in different shells around each nucleus for different elements. So if you have a look at this table, you should have seen this before, and for example, we start with hydrogen. Hydrogen has got one proton, so it's going to have one electron, so there should be one electron going around this first shell. Lithium here has got 3 protons, so if it's got 3 protons, the atom will have 3 electrons. You can only fit 2 on the first shell, so it'll have 2 in the first and 1 in the second, and the whole show should look like this. And hopefully this will be something that you've seen before, so we can see well the electrons fit, and it looks slightly crowded and messy, which is why we have this code at the bottom. So for example, for sodium it's 281, meaning there's 2 electrons in the first shell, 8 in the second and 1 in the outermost shell. But you need to see the patterns as well. So group 1 always has 1 electron in its outer shell. Group 2 all have 2 electrons in the outer shell. 3 has 3, and so on up to group 7, which both have 7 electrons in their outer shell. Group 0 is called 0 rather than 8 because we're saying is the next available shell there are no electrons in it, because if we called it group 8, well, neon and argon have 8 electrons in their outer shell, but helium can only have 2 electrons, but these all have a full outer shell. So the next task was to use what you'd learned before, recall the electronic structures of atoms, and now we're looking at ions. So we know what the electronic structure is, we've just looked at that, but the thing with an ion is all atoms want to be stable, and in order to be stable they must have a full outer shell of electrons. We know that group 0 are stable because they all have a full outer shell, 2 for the first one, 2,8 for neon and 2,8,8 for argon. So all of the other atoms want to have this full outer shell. So if we draw the electron structure when they've got a full outer shell, this is what it's going to look like. So group 1 have all lost the 1 electron in the outer shell. Group 2 have all lost the 2 electrons in their outer shell. 3 lost their 3. We're going to ignore group 4 because it's a bit more complicated for now. But then we go on to the non-metals. So the metals have all lost the electrons in their outer shell. The non-metals have got gaps. So in theory, fluorine could lose these 7 or just gain 1 to get an outer shell full. So non-metals fill their outer shell with spare electrons. So group 7 have all taken 1 electron in their outer shell. Group 6 have taken 2 electrons in their outer shell, and group 5 have taken these 3. So we can look at some other properties of them, such as the charges, because now there's an imbalance in the number of electrons and protons in each atom. So looking back at this now, if we go back to lithium, lithium has got 3 protons. The number of protons never changes. It had 3 protons, it still has, but now instead of having 3 electrons, it's only got 2. So whereas it was neutral, it's now got 1 extra positive to the number of negatives, so this is going to have an overall charge of +1. Beryllium has 4 protons but only 2 electrons, so the charge is 2 positive. And let's go to a different one, let's go to sulfur. Sulfur's got 16 protons, but now it's got 18 electrons, which means it's now got more electrons by 2, therefore it's going to be 2 minus. So if we just try and make this a little tidy and look at the different charges, we can see a nice pattern forming. All group 1 form +1 ions, group 2 +2 ions, group 3 +3 ions. And then if we look at group 5, we're now going to the non-metals. These take on extra electrons, so group 5 -3, group 6 -2, and group 7 -1. Group 0 no charge because they are the noble gases and they don't form ions under normal circumstances. So these are one of those things that you need to remember. I just remember metals form the ion of their group number, and non-metals, their charge added to their group needs to equal 8. So now we know the difference between the atom and the ion, we need to be able to construct half equations showing this change. So here I've got some ready for you. So lithium, this has got no charge, therefore it's a lithium atom, will become a lithium ion. Now lithium is in group 1, so it's going to be a +1, and it's going to lose this one electron in its outer shell. So it's a matter of learning that lithium will go to lithium plus an electron. Now let's do some non-metals. Now here we have O, oxygen, group 6. It's going to take in 2 electrons to fill its outer shell, which will make it a 2- ion. Now just to make it slightly more complicated, we know that O2 goes around in pairs, it's O2, so an O2 molecule will actually take on 4 electrons to make 2 O2- ions. Both of them are correct, it's just this one's a little bit more apt with it being O2 as a molecule. We then moved on to ionic bonds. So we've learned about ions and how ions are formed, and most importantly which charge different ions have. But an ionic bond is when oppositely charged ions are held together by strong electrostatic forces. So these are the key terms here that I've underlined. Make sure that you realise that it's something so simple. A sodium plus ion is going to be strongly attracted to this fluorine minus ion, and they're held together by a strong electrostatic force. Electro because it involves these charges, and static, there's no movement, they are staying together. So this is the process. Here I've chosen similar ones. I've got a group 1 and a group 7 element. Now sodium is going to get rid of the electron in its outer shell to form an ion, and then it's got this full outer shell, and chlorine has got 7 electrons in its outer shell, but it wants 8, so the two of them together will react, and basically the electron leaves the sodium, making this a stable atom, arrives in the chlorine, making this one a stable ion. Sorry, that was an ion. And there we have this sodium positive ion and this chlorine minus ion, much more stable, and this electrostatic attraction between them will make this an ionic compound. Depending on the atoms involved, they'll have different ratios that they will react with. So for example here I've chosen magnesium, which is in group 2, and it wants to lose 2 electrons. Fluorine is in group 7, it only wants to gain 1 electron, which means that 2 fluorines will be involved, as they will both take 1 electron each off the magnesium. So when we make magnesium fluoride, it has a formula of MgF2, and that's the reason why these formulae are different. It's just the ratios that are needed to balance out the electrons. So a slightly more complicated one, and you won't get anything more complicated this at GCSE. If we have iron 3, it's got 3 electrons it wants to get rid of, and oxygen in group 6 wants to take 2. So in order to make this balance out, the lowest common multiple of 3 and 2 is going to be 6. So 6 iron electrons go into 3 oxygen atoms to make Fe2O3. And then to make sure that it is an ionic compound and it's all balanced, when you've got the ions in, make sure that the overall charge is 0. So here for example calcium 2+, there are 2 chloride ions -1 each, so the overall charge is 0. That is a balanced ionic compound. The other type of bonding that we'd like to look at is covalent bonding, and covalent bonds occur between 2 non-metals. They share their outer electrons in order to fill their outer shell. So just like ionic bonding, they want to fill their outer shell, but as there are no metals giving away their electrons, they have to share them. So here we've got the most simple example. We've got a hydrogen atom. So here it is, it's unstable because it's not got a full outer shell. We're not drawing the nucleus, it's just this 1 electron when there should be 2. And here is another identical one, but you'll notice straight away we're using what we call the dot and cross notation, so we can see where the electrons are from which atom. Now these 2 unstable single atoms will combine, they will overlap their outer shell, and their electrons will go into this overlap, and this is a covalent bond. So if we look with respect to this hydrogen on the left, there are now 2 electrons in its outer shell, which means it's full, and then with this hydrogen here there are 2 electrons within its outer shell, therefore it too is full and they're stable. If we look at more complicated ones, here we've got chlorine, and again, note this, we only draw the outer shell, don't try and squeeze in the other shells inside. This chlorine atom, because it's in group 7, has got 7 electrons in its outer shell, and this one in group 7 has got 7 electrons in its outer shell, and this is unstable. So if they overlap their outer shell, they put 1 electron each in this overlap, they've now each got 8 electrons in their outer shell, so now it is a much more stable chlorine molecule. And just look, it's Cl2. As we saw with the last one, H2, these are molecules that we see and we recognise, and they don't hang around on their own, they go round in pairs. And now we can look at the slightly more challenging one, which is oxygen. Oxygen, the unstable version, has got 6 electrons in its outer shell because oxygen is in group 6. So if we have 2 of these, the only way to overlap to make sure that we have 8 electrons in each outer shell is they must put 2 electrons each into this overlap. So now each oxygen has got 8 electrons in its outer shell, but by the fact that we've now got 4 electrons in this overlap, this makes this a double bond, so it's often drawn like this. Instead of a single stick, it's this equal sign, the 2 bonds, and this occurs in lots of different molecules. Here we've got another diagram to show you, and this is nitrogen bonding with 3 hydrogens, a slightly more complicated molecule, and it can be drawn several ways. We can draw it like this, which shows more of the shape of the molecule. We can do a dot and cross diagram here, which we haven't got the circles of the overlap, but we can see the bonding electrons that are involved. The circles are for the hydrogens and the crosses for the nitrogen. Or we can just draw this stick here. Each single stick shows a single covalent bond. So as there are only 2 electrons in this bond, that's a single stick. The last thing with covalent bonds is you really must be used to drawing them and being able to work out the number of electrons in each atom and what the bonds will look like, and drawing the dot and cross diagrams. So I've just got these 3 here. You've just seen NH3, which is ammonia. We've drawn O2. Can you have a go at CH4, which is methane? So just pause the video on a piece of scrap paper, have a go, and while you're doing that, I'll draw it in here and then you can compare it afterwards. Okay, so hopefully you've had a go at that. If not, pause it now. Right, so let's just see what I came up with. So this is my wonderful, I'm struggling with my graphics tablet, I'm not very neat, but this is what the stick diagram should look like. It's a carbon in the middle with 4 hydrogens, each with a single bond coming across them because it's 1 electron pair shared. And then for the, wait for this is brilliant, the dot and cross diagram is awful. But what it should look like, which I've got off the internet for you, is this, which shows clearly the carbon in the middle, 4 overlaps with 4 hydrogens, and in the joining overlap there's 1 electron from the carbon and 1 electron from the hydrogen in each, which links to the single covalent bond between each there. Now, using this cheat of mine, go and have a look on the internet for these different ones, and you should be able to do them for CH4, NH3, H2O, as well as the diatomic elements like chlorine, fluorine, oxygen. Okay, thank you.